My name is McCluskey. I work at Google on Dataflow ML mainly. I'm out of Durham, North Carolina, so you'll see a lot of folks here from that office. We're talking about Python type hinting today, and in particular, we're talking about how Beam handles Python type hinting. This is one of those things that at best, developers don't actually pay attention to. These things should just work. But this is how you're kind of catching problems in your pipeline and avoiding issues that Python's type hinting can cause problems with. It looks like the ordering to my slides that I changed last night at like 11:30 did not get picked up, but that's okay. A little bit about me. I actually graduated from UNC Chapel Hill in 2020. I started at Google in July of 2020, so this month is my 5-year anniversary, which feels crazy to say. And then I started working on Dataflow in June of 2021. Over 4 years, I've seen a lot of changes come through to Beam. The community's grown. We've seen things like the shift to ML. I also have the very fun distinction of being, I think, the only person to ever accidentally delete the main Beam repo during a release. Everything's okay. It's fine. Danny saved me on that one, and we edited the history, so blame still works. But I have had a panic attack thanks to that. So if you ever make a mistake, just remember you didn't delete an entire Apache project. So when I'm not doing this, I'm a powerlifter, I'm a competitive fighting game player, I am a sneaker collector, I am a dog dad. That is my German Shepherd, Kenna. She's waiting patiently at home for me with a pet sitter. She will tackle me when I get home. So if you ever have any interests that you want to talk about, I will gladly geek out with you on them. So I'm going to actually jump ahead to this slide first. So Python, as many of you are aware, is not a statically typed compiled language. It is duck typed. What that means, if it walks like a duck, it quacks like a duck, it looks like a duck, it is a duck. We don't care what it actually is. So instead of direct inheritance, we have compatibility based on this subtype relationship we define. So a type is considered a subtype of some conceptual parent type if you have valid attribute values for everything the parent type has, and you implement the methods of the parent type. So it's kind of like an interface relationship in other languages like Java, but instead of explicitly declaring that you are implementing the interface, if you happen to implement it, then we're going to count it. This can get kind of messy, but effectively your type is the minimum guarantee of what you're providing as an object. Special case, this is important, the any type is compatible with everything, and everything's compatible with any, no exceptions, any type check or consistency with any will pass. This is great, but will cause some problems as we'll see later on. Oop. And then some quick definitions. I'll talk about static and runtime type checking. Static type checking in Python is your static analysis of your code. This is happening within your IDE. So you're sanity checking how your written code interacts with an object based on the type you hint. This prevents you from accessing fields or methods that an object isn't expected to have when you write your code. This is a good sanity check. But this doesn't impact runtime at all because it's Python. You can throw anything into that function and then you'll get a runtime exception. When we talk about runtime type checking, that's when you're actually programmatically checking your type compatibility during your code execution. This is really useful when you're not necessarily sure how functions chain together, like in a Beam pipeline where you're building a DAG dynamically. But same thing, it's still not necessarily reflective of actual types at execution. As a note, Beam has mechanisms to check types during pipeline execution. That's not what I'm talking about here. We're talking about type checking at graph construction in particular. So why do types matter? So the static checking gives you the sanity check within your do-fun definition. So when you have a do-fun written, this is within that function, your process function. You're checking to make sure you're not accessing something improperly based on the type you expect. That way, your code should make sense and should run within that do-fun. And then our runtime type checking gives us the sanity checks between transforms in a pipeline graph. So you make sure if your downstream transform expects an integer, you're handing an integer instead of passing it something else. As an aside, Beam Python also uses type hints to select coders. The fallback coder is just generic pickling, but if we can pick a more efficient coder and representation for your data, we will do so. But you need to tell us what it is first. So you apply type hints in a few different ways in Beam Python. I've kind of put these in order of like most to least recommended. You'll kind of see why as we go. So the first is PEP 484 function annotations. These are probably the most familiar if you've written Python. It's your colon and arrow syntax with your hints. So this is from the word count example in the Beam repository. You have your processing once you've gotten words out of your text corpus. And each individual element is a string. We're returning a string, and then we're using a regular expression. Talking too fast. We're using a regular expression function that takes a string and produces a string. This is sort of where your sanity check comes in. Within that method, you expect to be operating on strings. You're checking the types that the find all function is expecting. Everything's happy. So Beam also provides this method of method chaining for your hints with the with input and with output types methods that you can chain on Pardue declarations. This is really nice, largely if you're trying to narrow the types that are going into and out of a do fund that can operate on broader types. So if you have something that operates on any or produces any, you can use this to narrow the types within the check. This is really just for further sanity checking, make sure you're handling your types correctly. As you see, we define word extracting do fund, but we don't have those PEP 484 type hints. We define those, and then we say we're producing a string at the end. The problem is you don't get that static type check within your word extracting do fund, so if you start accessing an element improperly, you're not gonna find out until you try to run the graph. And then we have these function decorators. These are a legacy from even before Python 3 and before PEP 484 type hints were really a thing in Python. These are a way you can specify input and output type hints on a class. And this is great because it has the nice upfront what you're putting in and out. You can do this for composites, and this will specify the input to the composite and the output from the composite without interfering with the internal checks. The problem here is that these annotations override anything else you've put into the do fund. So if you do the 484 hinting or you do the method chaining, those get overridden by these annotations. So if you do both, which you should at least be doing the 484 hints, these can override any changes you make, and then if you break a type hint internally and you fix it, everything's gonna keep failing if you don't also fix the annotation. So now we're gonna get into the crunchy stuff within Beam internally. Beam uses internal type representations of common container types rather than the Python native versions. This comes from a couple things. First off, the same idea of this sort of predates the common Python type hinting. And then there have also historically been issues with serializing native Python types for our purposes with pickling. Those may or may not exist. Those are historical, and we've been making efforts to change what our default pickler is. So part of my job in the next 3 to 6 months is to see if this is still the case. But the way these currently work is you have 2 base classes that we inherit from to operate on these things. The type constraint class, which provides a consistency check method to see if, given a type, it is consistent with the type that class represents. And then a composite type hint, which takes parameters to a nested class and builds a composite based on what you've passed. This uses the get item interface, so the familiar brackets for a type. And then it builds a type constraint that represents what you've passed. It also typically contains a nested definition of a type constraint for that class. It's a little messy, we'll get into it. So here's what a type constraint for a dictionary would look like. You initialize it, you have your key type and your value type. We'll talk about what that normalized function is later. And then for consistency, we want to make sure that if you are given a type to check against a dictionary constraint, it's a dictionary, or implements dictionary. And then you want to make sure that the key and value are also compatible types. And then this is the messy composite version of this. I am all the way over here. So, as you can see, we have the get item. So when you parameterize this, it looks like dict and then the brackets, as you can see in the type error definition there. We're doing some input validation. You want to make sure you're getting a tuple of a key and value pair. You don't want to get more elements. There's also some further validation I've omitted here, and then you return the constraint, and that's what we operate on. But how do we get to this? So we process known container types into these Beam internal representations in the native type compatibility.py file. Known container types are built-in containers like dicts, lists, sets, etc. Things from the typing module, which are largely deprecated now. You should not use them apart from things like typing.any. We have, and then collections and collections.abc. Those are the more preferred collections and containers for use in type hinting now. Those are our known container types. So we have these things, we have a function, we get a type in, and we then start going through a list of named tuples that define what types we're looking for, how many subtypes could be nested within them, which is the arity of that type. And then we also have a matcher function that talks about, is this the type we want? And then if so, what internal representation are we going to? Let's see, okay. So our example matcher here, we're matching, is this a dictionary? So we're checking, is it a subclass of a dictionary, or is it the actual primitive definition of a Python dictionary? So the built-in dict type. Safe is subclass, as a note, is just calling Python's is subclass, but it swallows type errors because is subclass is very picky about what you pass to it. So that's just a wrapper that swallows the error. And then the example entry that we're looking for to compare, we have the type map entry that we have the matcher, we have an arity of 2, which means we expect a key and value type to be passed in with a dictionary, and then our type hint definition is that composite type hint discussed earlier. And then when we iterate through this list, we actually go through the list of matchers just in order. So we actually have to start focusing on the most specific type hint for an equivalent and then broaden out. So for example, a frozen set is a set, but it's also got extra things on top of it. So we have to check if a type is a frozen set first before we check if it's a set. Okay, so we've processed our hints down to something that Beam understands. How do we check if something's compatible or if two types are compatible once we have extracted the hints from adjacent transforms? So we have this is consistent with function that we try to leverage as much information as we've gained up to this point before we fall back to that built-in is subclass check. Once again, is subclass is very finicky about what you pass it. It doesn't do parameterized generics. It doesn't really like defined classes. So we want to use that as little as possible. So we have 4 steps here that we do in this function. We check our common cases. We call that normalize function we saw earlier. We check against the type constraints we've defined. And then last but not least, we fall back to is subclass if we have to. So is consistent with, this is the first part. So if the types are just the same, we have identical hints. We stop, we return true, we are done, no problem. The next block is there are some relationships that are defined in PEP44 around integers and floats and complex numbers. An integer is consistent with a float or a complex, and then a float is consistent with a complex. So we just handle that explicitly. And now we get into normalization of the type hints if we've fallen through to this point. This function looks very messy. I apologize. It's gotten bloated as we've changed things. So if none is a valid type in this context, and the type you've given it is none, we return a type-wrapped version of none that we can check against. Otherwise, we fall through to go to bare primitives. So if you say dict, list, set, frozen set, what have you, but you don't parameterize it, we throw an any in there so we don't have any issues. And then we fall through further to if it is one of those known container types as far as sources, so it's a parameterized generic, it's from typing, collections, collections.abc, we do that converting to beam type we discussed earlier. If we've changed that, we were able to do the conversion, we return the beam type. This is where things get a little tricky. If it's in those source modules, but we do not actually handle it, we didn't convert it into anything, it gets turned into any, so we don't fail a type check that should be correct. This is very convenient because it means we don't have to implement everything for correct type hints to be passed, but it causes a lot of problems. Recently, a contributor added support for sequences and iterables and doing all this explicit checking. That was really cool. The problem is at Google, a lot of people were type hinting that they were gonna get like a sequence or like a list when the guarantee from the Beam model itself was you were getting an iterable, which led to me changing about 150 pipelines internally to avoid workflows breaking. So this has some sharp edges to it, and ideally we're gonna get off this soon enough. There we go. So going back to the is consistent with check, we start running through the type constraints we define. Any, we pass it. If your class that you're checking against a parent class is a union, everything within that union has to be consistent with the parent type. So we check that. If it's just a type constraint, we call that consistency check we defined. Rows, we're checking against just the row type. If the instance that your sub is just a bare type constraint, we only check against object. There's some extra logic for regular expressions. Typing generics, if it's not a parameterized generic and it's made it this far, it's going to break is subclass. So we just return false. We just bail out and you have to fix your type hint, and then the is subclass check. Okay, that was dense, I know. It's a lot, but now I have to talk about the trivial inference module because more people need to know that this like monster of code exists in the code base. More people need to be aware. Trivial is the biggest misnomer in this code base because the trivial inference code in Beam Python is a very robust C Python emulator. We emulate underlying C Python bytecode for any untyped function. This mostly comes up for lambdas and map functions, and we determine possible return types. So C Python operations, if you've seen any sort of decompiled like assembly code, it's gonna look very familiar. You have an operation, you have an instruction size, potential arguments, and then each opcode has potential interactions with the stack, return values, any sort of branching. We have to emulate all of this to determine what possible return types come out of that lambda. So a note here, we're not actually operating on real inputs to these lambdas, we're operating on types themselves. So we don't care about, if this thing is a 0 or a 1, we just care, is it an integer? So things like additions, subtractions, what have you, we don't actually sweat, we just kind of keep going. But anything that interacts with the state of execution, we have to handle. So how does this work? We create initial objects to track our emulated state. These are called frame state objects. This has a representation of the stack, keyword names, and so on. And then we have sets of returned and yielded types that could be produced by the lambda. And then Python provides this package called the dis package. It's the disassembler package that pulls the actual underlying bytecode from CPython for a given function. And we pull that information, and then we organize it into a dictionary with the byte offset of each instruction as the key, and then the actual instruction object as the value. This contains what the operation is, arguments, that sort of thing. And then we loop over the program, and we emulate each instruction that directly impacts the state we track. Like I said, some things are no-ops for our purposes. There are also a lot of these things called cache operations that were introduced in Python 3.10 or 3.11. that they occupy space on the call stack and are not necessarily represented by an argument, but we have to handle them because if we don't, we will kind of seg fault in our emulation. And now here's where things get kind of funky. There are CPython operations that introduce logical branches. Jump if true, pop if false, so on and so forth. And you can envision a lambda where a branch will determine what kind of return type you have. If X is true, return an integer. If it's false, return a string. So we want to cover all of these branches. So how this works, we get to a branch, we actually save a deep copy of the current state of the frame, which is our do not branch case. We save it in a list of states that we store. We modify the active frame based on the branch case, so we now have split into parallel universes of branch and do not branch. We emulate the active frame until we complete it, and then we go back and get the save state we had, reset the program counter, and then we go to the conclusion of that branch, and we just keep going. Now, the very funny thing here is that for things like recursion, we only go 5 levels deep, so we give up at a certain point. But for these branches, we do it pretty exhaustively. Fortunately, lambdas can't get too complicated for the most part. Please no one try and break this, because I will be sad. But it's an option. So I know this was a lot. This was a lot of slides with code snippets and me rambling back and forth. There's a doc that was mailed to the dev list that I updated recently. Here's the short link. It has an overview of all of this. There are also permalinks into the code base that actually point directly to the classes I'm talking about. There are snippets for usage. There are comments from Robert Bradshaw about the historical context for these things if you're interested. I would highly recommend checking it out. That's also what I used to build these slides. I think the doc came first. So if you are interested, please take a look. You can also just ask me any niche question about this you want. I think very few people have dug into this. I appreciate everyone who does, because everyone finds bugs and has questions about why things are the way they are, and I love getting those questions. But yeah, I've been Jack McCluskey. I am JR McCluskey on truly every platform except for my personal Gmail, because someone took it somehow. So I have an Apache email you can hit me up at. I'm on Blue Sky, I'm on LinkedIn, I'm on GitHub, and I'm right here. So.